use the Feynman trick, shift the origin, and you can still continue. So yes, there's nothing totally intractable about doing this case. But in the order of the lectures I gave, you would get stuck. However, here's the thing. However, so I'm just using the self-energy thing to illustrate like every trick in the book that comes up routinely. However, sigma is equal to something like a real constant I'll tell you who it is in a second, minus plus p squared. I'm throwing away that 8m squared that I keep getting wrong.
Yeah.
Right? G squared integral dx, and then log m squared minus p squared x 1 minus x minus I epsilon. Okay, so however, our old friend, this case, where I'm below 4m squared, we saw that the answer looked like this. Okay, this was just that integral which had no p dependence in it whatsoever. Okay, so it's just some real number. But basically we had this function of p squared. It's this guy. By the way, if you worked harder, you could actually do the x integral. Try that. Just to know that I could get the absolute bottom line function. It is not very hard for you to just, basically this integral of log x, that's the hardest thing you ever have to do. You know what that is. Okay, so you can break up this into various bits. Is analytic as a function of the external momentum. It's an analytic function with just some sort of a branch cut somewhere or another, and an I epsilon prescription telling you whether for real p squared you should be above the branch cut or below the branch cut. It's a very simple analytic function of p squared. And it at least makes sense or makes mathematical sense for p squared greater than 4m squared. So we derive this in this regime, but here's a formula. The formula does not tell you which regime it was derived for, and it continues to make perfectly well plug in p squared bigger than 4m squared. Nothing would go wrong. The one thing that would go wrong is that since x times 1 minus x is smaller than a quarter, for x between 0 and 1, you can now, for p squared bigger than this can now be log of a negative number. And so you'd say, oh, well, see, I told you you shouldn't have used that formula. But I have the I epsilon prescription. It tells me exactly how to take log of a negative number. Okay? So there's no problem in applying it here. Okay? So it makes math sense with the I epsilon. Okay? So note that fact. Now, could it be true that that the result of doing the p squared thing honestly, whatever the honest answer is, could it be true that it's just this? Okay. So first of all, this sigma derived for p squared less than 4m squared is an analytic continuation when applied to p squared. So, doesn't mean it's right, but it does mean it has a name. The name is that if I continue to use this function, which was derived in a certain regime of p squared, if I actually use it beyond the regime in which I derived it to be correct, just because it's an analytic function and it makes simple sense to go, this is perfectly well defined for larger p squared. That's an example of an analytic continuation, of which complex functions are loaded with examples, that you've probably seen in math classes. But here, it's an analytic continuation to say that this thing is true here. Mathematically, you could just say that, and that would be that. That would be almost like a definition to say, look, I can extend, this is an analytic function, and I can extend its domain of applicability to p squared greater than 4m squared, and it remains analytic. It's great. But the question is actually the answer to the physics question we have over here. And here's the thing. Here's the plot. If I can look at the original honest expression and say that the true answer, without calculation, I just have to say, if the true answer is at least an analytic function of p, then it turns out that the theorem we're relying on is that if this is an analytic function of p, which agrees with this for p squared less than 4m squared, and this is another analytic function of p squared, which trivially agrees with this for p squared less than 4m squared. Two analytic functions which agree on this big region, p squared less than 4m squared, are unique. In other words, analytic continuations are unique. Okay? So let me say that again, and then I'll try and write it in some cogent way. This integral certainly looks like that for p squared less than m squared. So you can, but it of course exists for p squared greater than 4m squared. It is an analytic function, and so you can think of this integral as an analytic continuation of this sigma for p squared less than 4m squared. Okay? It's an expression that makes sense beyond that region. So it's an analytic continuation in that sense. Just taking this thing at face value and continuing to use it outside this regime is another analytic continuation. There is the theorem we're relying on is that analytic continuations are unique. Okay? In which case, whatever this thing is, for p squared bigger than 4m squared, it just has to be this. It just has to be this formula. Okay? A priori, you could have said, yes, it's mathematically well defined in this regime. This thing is also mathematically well defined. It's just that I haven't computed it. But I don't see why the two are the same. But the fact that they're both analytic continuations from the regime p squared less than 4m squared means they have to be the same. That's the plan. There's a question. No. Okay. So we first have to just check that this is actually an analytic function. So, first of all, if I didn't have to do this integral, then I would be, so some fixed q, then this would just be some rational function of p, and it would be analytic. In fact, you might say, wait, well, it's analytic, but you're being a bit sloppy. There's even a pole, actually a pole there, some sort of pole, and if you think of it as a function of p, there's some sort of pole in p. But it's certainly analytic in a big chunk of complex p space. I mean, even the real p is that, with that I epsilon in place. Even for real p, I'm not hitting an actual real pole. The pole is in the complex plane. But you can see that there is a big regime in p in which this is perfectly well defined for complex p. Okay. When I do this integral, all hell can break loose if I no longer have convergence. That is, I can't analyze everything as saying, oh, look, it's just a sum over q's, and mostly these q's are pretty finite-looking numbers, so it's like this case again. And in fact, that terrible thing comes to pass, because this is a highly divergent integral. But with all these regulators thrown in, or if you want, by differentiating a few times, I do have something which is a convergent integral. And indeed, I can just inspect the integrand and say, this is an analytic function of p. By doing this integral, I still have an analytic function of p, even though I haven't done the integral yet. If I'd done the integral, then I don't need to do all of this dancing. I would just write down the answer. So what we're doing is we're inspecting the form of the integral that remains to be done in that regime, and saying, it's at least an analytic function of p. Okay? Now, if p squared is less than 4m squared, this is exactly the integral we started with many lectures ago, and it does agree, and in fact it gave us this result. So this expression is therefore an analytic function of p squared. It agrees with that for p squared less than 4m squared, but it's analytic even beyond that. And in that sense, this is an analytic continuation of the p squared less than 4m squared case. This formula is also an analytic continuation of itself when restricted to that. So that's the statement that they're both analytic continuations. Then the result that I'm using, which I think has some fine print in terms of if you have multiply connected regions of the complex plane and so on, but we don't. We basically have a good chunk of the complex p-plane in which we have actually calculated this result. And the region that we're going to, which is just this. By the way, you can just think of this as even real part of p squared less than 4m squared. That Wick rotation and all that stuff we did, that would have made sense for complex p, just as long as the real part of p squared was small enough. Okay. So we're just going from a big chunk of the complex plane to the whole complex plane, and there's no, there's only, there's no sort of, there's no holes in the domain of the complex plane. So this is where the theorem of complex analysis, which says that analytic continuations are unique, comes in, and says you do not need to recalculate this all over again. So let me just write a sentence and just say, I'm going to take that question. Hang on. The loop integral expression implies that analyticity in P. So for P squared greater than or less than m squared, or m squared. So by uniqueness of analytic
So here, the boundary between these two functions seems to me just a point.
What do you mean by boundaries? The domains.
Yeah, domains. So first you had this function which breaks down at p square equals to 4m squared. And then you are analytically continuing beyond the point, which is not clear to me. Because you usually you do analytic continuation beyond a boundary which divides the whole complex plane into.
So you're saying, look, I don't like the fact that the boundary that we're talking about is I want to know the answer here, and I've learned the answer here, right? But in fact, I don't need to even use the answer all the way up to this point. I could just take some set here and say, I know the answer here, miles in the interior. But this is the answer, and it continues to be, it is the unique analytic continuation outside this ball. You don't need very much of the complex plane, like just some open set or something. I don't know what the exact techno speak is. I have to think about it. But basically, like if I were to try and prove this, I would be trying to use the Cauchy equations.
But doesn't it depend on the fact that analytical functions are uniquely defined by the boundary? So if they agree on the boundary and there is an analytic continuation, so the continuation has to be unique because analytic functions are uniquely defined at the boundary by Cauchy's integral theorem.
Yeah, you seem to be using a kind of like, if I tell you the boundary behavior of a function and I tell you it's also analytic in the interior,
yes,
then I know the function.
You know the function at any point in the interior.
But I don't think I'm using that aspect of the story.
But the uniqueness, I think, uses that fact that if you have a function and there is another function which matches at the boundary, and this can be continued to the other side of the boundary, then that is unique analytic continuation. As far as
I think it's open set. I'm almost positive that if you know that if
It's
you know it's analytic on some open set, you can uniquely continue it to.
That's what I was remembering from my youth.
Yeah.
But I think I even might
To
go
the
with the
rest of the
strategy for
complex
proving
plane.
it, which is to use Cauchy's equation.
Unless there's poles. I think if
Unless
there's,
they're poles, yeah.
if there's poles, then
Poles are effectively like, you see, you can always say, well, let me cut out that region where there's a pole. But that makes a hole, and that makes the space no longer simply connected, and then there are some. But in this kind of thing, where there's no such multi-connectedness, I think it's just unique full stop.
I mean, you can even do it when there's poles. Like,
You can,
Like the
you
game
can,
of
sure.
that's what's it.
Yeah.
I think a quick question.
You can doctor the thing, remove the pole. I mean, there are many games you can play and continue to use the basic result. But I think for you math, the math experts can go away and do it. I work on a simpler philosophy. If I know how I would start the proof and I remember it from 30 years ago, then I believe it to be true. I know how I would start the proof that I'm talking about, and I do remember it from 30 years ago, and so I must be right. But you can try. I'll leave it as an exercise. If you don't like it, do it the hard way. But this is one of those cases where analytic continuation was different.
Yeah, so I had a question about how we know it's analytic. So we say that if we have a convergent, if we can write a convergent integral expression, that means it's analytic. And then we had an argument where the reason that we have this unique integral expression is because you can do the two derivatives. Is the fact that you're able to do those two derivatives and then integrate back up, does that include an assumption of analyticity? Or is that?
No. Think of it like this. Suppose my whole goal in life was to calculate the second derivative of sigma. Okay? Then I would just look at the second derivative expression of this and say, well, look, perfectly convergent integrals, no problem, and the integrand looks pretty analytic to me, and so it's just an analytic function of p. And then I write this expression, and I take two derivatives of this. Okay? And I'd stare at that, and I'd say, well, that's an analytic function, and it extends itself to the whole complex plane. So then I'd say, the second derivative of that must be the analytic continuation of the second derivative of this. and by the uniqueness of analytic continuations, that is, the second derivative of this is my answer to d squared sigma. Okay? So now I've got the answer to the second derivative. Now I will integrate twice. I'll get two integration constants, a plus bp squared. And then I'm done.
So
You're done in
you're
that, you see
assuming
that order?
that your ultraviolet behavior doesn't somehow introduce and like a non-analytic thing in that argument.
You are assuming that no, I don't think I am. I mean, I wouldn't mind assuming that, and we're going to see later that that is actually correct. But let me see if I can say it without assuming anything. So what I'm saying is that dp squared of sigma is equal to an integral, which, however, is totally finite. There's no issue with the ultraviolet, and so this thing is analytic in v squared. Okay. Then there is an expression which is d squared p squared of this log t squared x 1 minus x blah blah blah. And this is also analytic in p squared. So the statement that we need is in this expression here. Before I did any analytic continuation, we just need that this is insensitive to the UV, by which I mean any heavy particles, etc., etc. I don't need to talk about it. This expression makes sense without mentioning anything about the far ultraviolet. Okay, and indeed, if you did put some heavy particles in from the far ultraviolet, and they came as part of the analogous diagrams would be order 1 over lambda, or 1 over lambda squared. Right, because by differentiating enough, I'm just getting some finite. I think we did this once where we said, if you think of sigma as equal, if sigma is made finite by the naive diagram plus new physics diagrams. But if this thing is already UV insensitive, say if I can take two derivatives, then this thing actually has to be, if this thing is UV insensitive, then this thing is actually going to be not UV insensitive. It's going to be UV insensitive, meaning it's dropping like 1 over something order 1 over lambda. Okay. And that came by noting that whatever the form of new physics is, it's got heavy propagators. That was the only insight. We didn't say exactly what type of thing. We just said it has heavy propagators, and so as soon as it's part of convergent integrals, then those heavy propagators are just going to be 1 over lambda. Okay. If you have something that looks like q squared minus some lambda squared or something, the q squared is not climbing up to sort of do cancellations. If the q squared is sort of being kept by convergence too low, then these things are just small. So all we're really saying at this step is that this second derivative is actually insensitive to all the new physics. Here's another expression. But if it's insensitive, this integral happens to equal this by explicit calculation in some region here. It's totally insensitive to ultraviolet. I've factored that issue out of the whole game. And so they must just be equal more generally. Now when I integrate by parts twice, all I can get, look, I've got the general p squared, here it is. So all I can have is a plus bp squared. And that's it. Okay, and let me just do one line. So I would like you to be as comfortable as you can with this, or just work on it by direct attack. It's up to you. Okay. But here is the message for the next lecture. I think the thing that changed, you know, it seems like not much has changed. You got the same damn formula. What's the problem? But actually something has crept in, which is the fact that this can go negative. You're taking log of negative numbers, and that means that for the first time, the self-energy can have an imaginary part. Okay, and this is the thing that's going to be of great significance to us. If you like, self-energy was part of some sort of energy of the particle, and now it's going to have an imaginary energy, and we have undergraduate quantum mechanics associated that with decaying particles. So we're starting to see how that comes about blow by blow, but basically we're getting this. So first, where is this imaginary part coming from? I'm taking the imaginary part of this log, and it's log of a negative number, which means e to the I pi minus 1. Yeah, so it's that. And so what we have is a step function to insist this only ever happens if you're negative. Okay, so this step function just says that I am taking log of a negative number. And so log of a negative number, you're going to get the imaginary part being I pi or minus I pi, depending on how you, right? You're taking log of a negative number. So when you're taking the phase that you get, you can either go like that, or you can go like that. But this I epsilon tells you which way to go. Okay, it tells you how to break the tie given by the branch cutter. And so that's the answer. With a minus pi, and this is determined by the I epsilon prescription. Okay, so exercise, make sure you understand that sign, because that sign, unlike all the other signs in my lectures, that one is important, unless I got it wrong. And so what this says is that the imaginary part of sigma is less than 0. Okay, that's the sign that's going to be important. And so the question is, what is the meaning? Okay, and I'm already telling you. It's like an imaginary energy. And we're all used to, in quantum mechanics, having this as the energy. But then if you have an imaginary energy, like some imaginary constant like that, then this would look like e to the minus I dt and e to the minus gamma t over 2. And if this is the amplitude, if you square it, this phase factor will go away, but you'll get something which looks like a decaying exponential. And that's because the particle is actually decaying on you. This is how it gets modeled. So we're going to see how that works, and we're going to slice it and dice it in many different ways. And it's a very beautiful way in which a diagram that apparently, taken at face value, is not about decay. It's about just continuing along, right? But secretly it knows that this could have happened. Okay? And so we need to understand what this word "it knows" means technically, but we're going to go into it. Okay, so let's stop there. And it makes some of these undergrad things, these rules that you learn by heart, very clean.